Hello everyone, we are from Team 6 and today we are going to present our team assignment question 3. And this team consists of 4 members, which is Bei En, Afiq, Yu Xuan and Poh Yee. Here is question 3 and there is 2 reactions take place. For the main reaction is 1 mole of propane react with 3 mole of water vapor to produce 3 mole of carbon monoxide and 7 mole of hydrogen gas. While for the side reaction is 1 mole of carbon monoxide with 1 mole of water vapor to produce 1 mole of carbon dioxide and 1 mole of hydrogen gas. And this reaction was take place in the shell and tube reactor, and we are given that the zinc and propane was fit in a molar ratio of 6:1 at 125 degrees C, and the products was emerged at 800 degrees C, and all the propane was consumed complete consumption. And the hot gas stream is fit at 4.94 meter cube per molar of propane, and it was entering at 1400 degrees C and leaving at 900 degrees C. And we require to specify the basis and the reference condition used. And after that, we need to calculate the molar composition of the product gas, and assuming the heat capacity of the heating gas is 0.04 kJ per mole degree C. After that, we need to draw the process flow diagram, and taking 1 mole of propane feed into the reactor as the basis. Since there is 1 mole of propane feed into the reactor, so there is 6 mole of water vapor feed into the reactor. After that, we label the thermodynamic properties on each stream and the unknown molar on each stream. After that, we label the specific enthalpy of each system at each stream. Then, don't forget to label the heat transfer from the hot stream to cold stream. We proceed to the extent of reaction DOF analysis. List out 6 unknown and 2 independent reactions, and minus with 5 reactive molecular species and 1 non-reactive species. And there is 1 process spec, which is the gases is fit at 4.94 meters square per mole of propane, and the energy balance equation was used. We sum up the numerical, we will get 0. Since DOF equal to 0, the unknown can be solved.
So for the mole balance part, we use the extent of reaction method. So the upper reaction is zeta 1, the lower one we consider it as zeta 2. So since all propane is consumed, as mentioned in the question, N1 is equal to N out of propane. So N1 is equal to 0 mole. So the general equation of extent of reaction method is N out equal to N in plus minus coefficient of zeta. So for propane balance, N1 is equal to 0, so we substitute 0 and then equal to 1 minus zeta 1. So minus is because propane is the reactant. For H2O balance, N2 equals to 6 minus 3 zeta 1 minus 3 zeta 2. So we substitute zeta 1 that we get from the first equation. So the finalized version is N2 equals to 3 minus zeta 2. And it goes the same for CO, H2 and CO2. We substitute all the values, all the known values, which is zeta 1. So for CO, N3 equals to 3 minus zeta 2, H2 balance, and 4 equals to 7 plus zeta 2, and for CO2 balance, and 5 equals to zeta 2. So this is for the heating gas equation. As mentioned in the DOF analysis, we have 1 more additional equation that can be used to solve all the unknowns. So heating gas, we assume ideal gas. So we use the formula of PV and RT. So N equals to PV over RT. So we substitute all the values. So pressure is 1 atm, volume 4.94 we get from the question, and then minus times with 1000 liter, and then we divide with gas constant and the temperature in Kelvin. So for N6 we get 35.98 mole.
So before we start to draw or do our table, we have to set our reference set first. So here, for this question, we set the hot gas reference set, which is same as the input stream of the hot gas, which is the gas phase 400 Celsius and 1 atm, and carbon solid 25 Celsius 1 atm, hydrogen and oxygen at gas phase 25 Celsius 1 atm. So after this, we can input and insert all our value and information into the table. So since our input stream of the hot gas is similar or same with our reference set, so we can set our hash in equal to 0 because there's no enthalpy change in the input stream. So next we can proceed with our calculation. So to calculate hash 1, firstly we have to draw a hyperpole first, and we have to determine the heat of formation to achieve the C3 hash 8 at gas phases 35 Celsius and 1 atm, followed by the hash A, which is the enthalpy change due to the difference of temperature. So this is a step to calculate hash 1. For hash F, we can directly get it from the table B1, and hash A, we can get a value, the CP value from table B2, and calculate it by equation of CPTT. So we can get the final answer for hash 1. So next, hash 2. Same as previously, we have to draw a hyperpole first, and to get a value of heat of formation, followed by the hash A. So for the hash F, we can directly get from table B1, while for hash A, we can directly get from table B8. But since there's not temperature of 125 Celsius in table B8, so we have to do interpolation to get the hash A at 125 Celsius. So we add both of them and we can get the hash 2. So to calculate hash 3, same as previously, we have to draw the hyperpole first, and to get the hash F heat of formation from table B1 and hash A from table B8. So next, for hash 4, draw a hyperpole first and get the heat of formation of CO from table B1 and followed by the hash A again from the table B8. So we can calculate the hash 4. So to calculate hash 5, since hash 2 is the elemental species, so hash 2 hydrogen don't have the heat of formation, so we can directly calculate the enthalpy change due to its difference of the temperature. So we can get the value from B8. To calculate hash 6, same as previously, draw a hyperpole first and get the heat of formation from table B1 and the hash A value from the table B8, and add both of them, we can get the hash 6. So lastly, to calculate hash 7b for the hot gas, to achieve the gas phases and 900 Celsius at 1 atm. So since the CP value given in the question, which is the 0.04, so we can directly use the CP equation, CPTT equation, to calculate the enthalpy change.
Since we cannot solve the unknowns by using mass balance equation only, we need to involve energy balance. Before we write the energy balance equation, we're going to write some assumptions. First is its steady state flow. Second is we will neglect potential energy, kinetic energy, and work. So this three will become 0. Then we write the energy balance equations. So this is here. The question given us that the process is adiabatic. Q will equals to 0. So at the end, we will get the total change of the enthalpy of the whole system is equals to 0. And we know that the changes of enthalpy have this formula is the total outlet of N times H minus the total inlet of N times H. We rearrange that, bring the inlet to the left hand side and bring the outlet to the right hand side so that we can calculate more easily. After that, we will substitute all the values that we calculated previously inside this equation. You can see this, we have the unknowns in terms of the extent of reactions is because we use this as our unknowns previously. So we are going to substitute, this is the N, and then this is H of that species. After we get the value of the extent of reaction 2, we can solve N2, N3, N4, and N5. First, we will write the equation that we previously write from the previous slide. So now we're going to substitute 2.015 into all the extent of reaction inside. And then for N2, after we substitute and calculate, we'll get 0.958 mole H2O. Using the same method for N3, N4, and N5. After this, calculate the total mole by sum up all these 4 unknowns together, and this is the output stream total mole. We will get the value is equals to 13 mole. This is useful for our last steps for calculations. The purpose of calculating the total mole is because we want to find the molar composition of each component in the output stream. So to find that, we're going to find the H2O first. So 0.958 is the mole of H2O in output stream. Divide by the total mole of the output stream times 100%. And we will get 7.58 mole percent H2O in vapor. By using the same method, we're going to find the CO. CO also has the same mole as H2O, 0.958. So we'll get the same answer, 7.58 mole percent CO in gas form. Next, we're going to find the H2 molar composition. The mole of H2 is 9.015. So also divide by 13 times 100%. We will get 69.35 mole percent H2 in gas. And last but not least, we have to calculate CO2 molar composition. The mole of CO2 is 2.015. So also for this, we're going to use same method. And the answer is 15.5 mole percent CO2 in gas. The red color is the final answer we get in these questions. Hopefully this can help you for your understanding.